Hi, this is Dave Johnson with another edition of Math Off Topics. Today I want to do a problem that's not only math, but also physics. And you remember, the math that you're learning is going to be applied to engineering problems as well as physics problems and other kinds of problems. And indeed, calculus was invented to solve physics problems. So, and this problem was brought to me by one of my calculus students. And it was interesting because, well, my intuition on the problem, although I do have a background in physics, I looked at the problem initially and was a little, confused at first. And so I thought, well, this would be a really good problem to share with students. So let's get into it. And if, by the way, if you're not comfortable with the physics, don't worry because I'll show you everything that you need to know. So we're trying to maximize the angular acceleration of a system. This system consists of this rod here, which is pivoted at the left end. And there's a mass, a block that's sitting on top of the rod. And gravity is pointing down. You can see the force vector for gravity pointing down toward the center of the Earth with uh, the gravitational acceleration g, which at the surface of the Earth is 9.8 meters per second squared. You might remember that if you've had physics. And if you haven't, don't worry. But what we want to do is we want to figure out what x has to be. In other words, how far is this block going to be away from the pivot point, somewhere along here, to maximize the angular acceleration. Now, what do I mean by the angular acceleration? Well, say this thing starts from rest and it's rotating, starts to rotate because of the effect of gravity. Well, we want that rate of rotation to not only the rotation itself, but the acceleration of the motion to be maximized. And I've labeled the dimensions here. The length of the rod is L, its mass is M1, the block has mass M2, and it's a distance X from the pivot point. And I've also labeled in red the forces that are acting on the block and the rod. So the rod has a force m1 times g, and it acts at the center of the rod. That makes sense because of the symmetry of the rod. We're assuming that it's a uniform rod, maybe metal or wood or whatever it is made of. And likewise, the block, it has a force that's acting on it, m2g, that's acting at the center of the block toward the center of the earth. Okay. So we'll come back to those forces in a moment. We're also told in the problem that all of these dimensions, not x, but the L, the M1, the M2, and the G, we're just going to set them equal to 1. That makes the problem easier to compute. You can also do the problem without making this assumption. And although there are more symbols involved, it turns out that those are all constants. So from a calculus point of view, they don't really affect anything. There's still only one independent variable in this problem, which is the x. Okay, and the angular acceleration that we're trying to maximize is this alpha here. Okay, so what's the physics? Well, the torque acting on the system is the moment of inertia, and if, those are big words, and don't worry if you don't know what they mean. I'm going to say them, and then we're going to write the appropriate formula, and we'll set this up, and you'll know exactly what's going on. So, moment of inertia times the angular acceleration. So, the moment of inertia we typically label capital I, and the angular acceleration is the alpha. It's often a Greek letter when we're in rotational systems situations in physics. We often use Greek letters instead of the ordinary Latin letters. Um, and tau, this is the Greek uh, kind of equivalent to our T. The tau represents torque. Okay, so torque is equal to moment of inertia times angular acceleration. Now, how do you figure out what these things are? Well, I'm just going to tell you, right? So let's think about the rod first. So because it's pivoted at the end, its moment of inertia is 1/3 times its mass times its length squared. So 1/3 m1 L squared. And the moment of inertia of the block, a distance x from the pivot point, its moment of inertia is its mass, m2 times x squared, x being the distance from the block to the pivot point. Okay, so the total um, moment of inertia, and let me write that here. So I, and that's going to be the total moment of inertia. It's the moment of inertia of the rod. So 1/3 m1 L squared plus the moment of inertia of the block, which is m2 x squared. Now, we also need to figure out what the torque is if we're going to solve this problem for alpha, and then we're going to maximize it. And you can already look ahead here a little bit. Once we have alpha in terms of x, then we're going to differentiate with respect to x. That's what you do when you optimize, when you maximize or minimize, you take the derivative and set it equal to 0. Well, okay, so the torque, so the tau, and I write that with kind of like a T, except that I put a little curvy top on it. That's just how I write my taus. It's the force. So in this case, let's do the rod first, m1g times the distance from the pivot point at which that force acts. So it's not L because L is the total length of the rods. It's L over 2, which is where the force acts. So m1g times L over 2. So let me write that. So m1g times L over 2 plus, so we're going to get the total torque here, plus the torque for the block, which is the force times the distance that the force acts on from the pivot. Now, life is a little bit more complicated than that. When you take the physics course, you'll see what I mean. But for now, we can just write this as m2g times x, because x is the distance. And now we're pretty much set up. We need to impose our constants. M1, L is 1, M1 is 1, M2 is 1, and G is 1. So let's go ahead and plug all those in. So M1 and L are 1, so we get 1/3 from the first term in our I, plus, and then M2 is 1, but X is not 1. X is our independent variable, so I'll write this as X squared. And then our torque is going to be, so M1 is 1, G is 1, L is 1, so we get 1/2 from the first term, plus, and then again, M2 and G are both 1, so we get X for our second term. And we're solving this equation for alpha, so alpha is equal to tau divided by I. So let me rewrite that down here. Alpha is equal to tau divided by I. Tau is the torque, and I is the total moment of inertia. And so this is equal to, well, we got 1/2 plus x divided by, and then the I is 1/3 plus x squared. Now, from here, it turns into just a basic calculus problem. But I do want to mention, so I said at the beginning of the video that there was something that was puzzling me. Um, I was thinking, and this was a bad intuition on my part, and I'm not perfect. I looked at the problem and I said, well, if you want to maximize the angular acceleration, you put the block all the way to the end because that would maximize the torque. Okay. If you maximize the torque, well, that seemed to me at the moment that would maximize the angular acceleration. Because for a given fixed moment of inertia, you maximize torque that's going to correspond to a maximum angular acceleration. It turns out that it's not quite that simple because, and I realized it right away as I even said this to the student. And so it turns out that you don't want to put the block all the way at the end. Why? Well, because, and let's think about this for just a moment, if you increase x in the angular acceleration function, so you increase x, that increases the numerator, but it also increases the denominator. In fact, it increases the denominator more once x is past a certain point. And so now it's a little bit more complicated than that. We're not going to get into all of that in this video, but if you increase x, you're going to also increase x squared. You're going to make the denominators bigger, and so that makes the overall fraction smaller. So you're actually reducing the angular acceleration. And that's not what you want to do. You want to maximize the angular acceleration. So, but let's do the calculus. And in fact, that's really, I mean, sometimes you can't rely on intuition. You need the math. And I'll come back to this in future videos a lot, but you really do need the math in order to understand what's going on in these problems. So how do we maximize alpha? So we're going to find the derivative of alpha with respect to x, so d alpha dx is equal to the bottom times the derivative of the top. So the derivative of 1/2 is 0, the derivative of x is 1, so we get a 1 there, minus the top, so 1/2 plus x, times the derivative of the bottom, so the derivative of the 1/3 is 0, the derivative of the x squared is 2x, divided by the bottom squared, so 1/3 plus x squared, squared. And we set that equal to 0. And now we want to solve this equation for x. The denominator here cannot be 0. So no matter what x is, the 1/3 plus x squared is going to be something other than 0. And when you square it, you're going to get something other than 0. So I can multiply both sides by that denominator. So we get 1/3 plus x squared minus, now let's just go ahead and multiply this out. So we get the 2x times 1/2 is x, and then distribute the minus sign. So we get minus 2x squared, and that's going to equal 0. And if we combine like terms, on the left side we get, so x squared minus 2x is negative x squared minus x plus 1/3 equals 0. I like it when we have a positive coefficient on the x squared, so multiply through by -1, we get x squared plus x minus 1/3 equals 0. Now, all of you can solve this quadratic equation. This cannot be factored, so use the quadratic formula. And when you do that, and I'm just going to look at my answer here. So x is equal to 0.2637626, and my physics teacher friends will be upset that I use too many decimal places. So let's maybe round this to, say, 0.26. And so that's 0.26, which is about a quarter of the way down this rod, because remember L is 1. So, and if you're not convinced, let's go back and look at this alpha function. So if x is 1, it turns out that, um, and I've done the calculation already. So if x is 1, the alpha ends up being 1.125, if my arithmetic is right. And if x is 0.26 something, let's just call it 0.26, then the alpha ends up being about 1.89, or about 1.9, let's call it 1.9. So obviously, if you put the block all the way at the end of the rod, you don't get the maximum alpha. You only get the maximum alpha when x is something less than 1. And that's what the point of this problem is. I will mention one more thing about this problem. It turns out that g, which we set equal to 1, ends up canceling when you do the derivative. And so you're going to get the same acceleration no matter what g is. And so that's one of the reasons why we can set g equal to 1. Or now you don't want to ignore it entirely, but by setting it equal to 1, we aren't changing anything. So I hope this has been helpful, and hope you found the problem interesting like I did. If so, subscribe if you haven't already, and give the video a like if you feel it's worth it. And I will see you next time.